Moving to our next talk, machine learning-based neuroimaging biomarkers for cognitive functioning. Are they applicable to children with attention deficit hyperactivity disorder? And our speaker is Farzane Lal Khakpoor from University of Otago.
Hello, everyone. Thank you for joining us today. So I'll be presenting about the applicability of population-based neuroimaging predictive models of cognition to children with ADHD. So to start with, cognitive functioning involves attention, memory, reasoning, and many other functions that are necessary for our daily life and overall well-being. And in neurodevelopmental or psychiatric conditions such as ADHD, we see prominent deficits in different domains of cognition, which means that cognitive functioning is a strong candidate as a psychiatric phenotype. Also, at the neural level, cognitive functioning is underpinned by a widespread neural basis that is not localized, and it's more related to a distributed network, white matter integrity, and also the overall functional efficiency of the brain. With that being said, one goal is to use this neuroimaging information as a predictive tool to predict cognitive functioning as a psychiatric phenotype. And also recent studies has used machine learning plus combining multiple neuroimaging modalities to predict cognitive functioning, and they have shown a boost in performance. This does not mean that, so the overall performance does not necessarily guarantee success in specific groups within the same population. So that's one problem. Another problem is that usually models that perform well internally might fail in external unseen data sets. So to address and investigate these two challenges, we used ADHD as our testing case. And this is not only because of its high prevalence as a neurodevelopmental disorder, but also because it's been associated with lower cognitive performance in different domains, and also widespread alternations in brain structure and function. So here you can see a figure from ABCD that we analyzed that shows the gap in cognitive functioning performance between non-ADHD and different definitions of ADHD, which aligns with what we know from the literature. Okay. So when we see that difference in cognitive performance, we thought that, okay, now that we're building these multimodal models of based on population-based data, do they generalize to people, children with ADHD or not? And we had 4 specific questions. First of all, we wanted to see that whether our models capture the distribution difference that we saw in the previous slide for the observed cognitive functioning scores. And then if they do, would our models perform similarly, or would the performance of our models be comparable between ADHD and non-ADHD children, or do we have to train specific models for each of them? And finally, I said that there is an overall boost when you combining multimodal neuroimaging data. But do we also see this within each of these ADHD groups or not? And finally, we want to see whether these findings hold in our external data set. So to do this, for the internal validation, we used ABCD baseline data that is collected from 21 locations or sites across US. And we train models, we build models on the training folds of this data set and then apply them to the test folds and then compare the test performance between ADHD and non-ADHD children. And then we used another smaller data set as our test set for external validation. And what we did is that we used some of the models that were trained in ABCD and directly applied them to this data set and then compared the performance between individuals with and without ADHD. So for ABCD data set, we used Cordova and colleagues' 2022 paper to create the tiers of ADHD. The first tier was based on parent report, present symptoms of ADHD. Tier 2 exclude comorbidities. Tier 3 included the teacher's ratings, and Tier 4 had 2 more additional scales as filters. So we used the total cognitive functioning score from NIH Toolbox as our target measure for prediction, and also created 81 sets of neuroimaging features, including different task contrast, functional connectivities from both resting state and task, and also a list of structural MRI and one DTI-related feature. For our external validation data set, they already grouped participants into non-ADHD and ADHD group using clinical interviews and scales, and we used the same grouping for our analysis. There they had the full IQ scale from the Wechsler test, and we used that as equivalent for the total cognitive functioning scores in our model. For our external validation data set, we only had 13 sets of features, which is much more limited than what we had in ABCD data set, and also the tasks were not identical. Anyway, we created task contrast, functional connectivities, and structural MRI, whatever that was available. So when it comes to modeling, we used a leave one site out cross-validation, and we trained 81 elastic net models for each of those 81 sets of features in internal validation, and then we got the predicted values of these single models, and then we stacked them into different combinations. For example, stacking all of them together, stacking only tasks, stacking only functional connectivities, and so on. And then we used these stacked sets of features to train random forest models, and then we got the predicted values from our stacked models. So for the external validation, out of the 81 single models that we trained from ABCD, only 10 of them was applicable to what we had in the external validation. We got the predicted values out of these models, and then we again stacked them into different combinations and used the applicable stacked models that were trained in ABCD to predict the cognitive functioning scores. Okay. So as for the results here, you can see that the distribution of predicted values that we got from our top performing model follows the same significant difference in that we could see for the observed cognitive functioning scores. And also, if you look at the effect size are also closely aligning with the ones that we see for the observed cognitive functioning scores. And in the external validation, we saw the same pattern of significant difference for both observed and predicted values. However, the effect size is much smaller, as you can see for the predicted ones. So here you can see the ranking of stacked models based on their performance in our non-ADHD group. And on the right panel, what you see is the bootstrap confidence interval for the comparison between non-ADHD and each of the ADHD tiers. So if the bootstrap interval passes through the 0 line, that means that there were no significant difference revealed between non-ADHD and each of the ADHD tiers. Based on this, we can say that all of our stacked models showed no significant difference between non-ADHD and tiers 1 and 2. And this was the same for tiers, for majority of them for tiers 3 and 4. And also, what you can see that mostly functional connectivities are the ones that are performing much better, and they are highly ranked. So the models that are highlighted here are the ones that were applicable to our external validation set. And there you can see that 6 out of 9 stacked models, again, showed no significant difference between non-ADHD and ADHD group. And another interesting observation was that unlike a spatial and back contrast, verbal and back contrast performed significantly worse in ADHD, even though they were both applied, the same model were applied to them from ABCD. And this might be because the spatial and back task in external validation is more close in task demands to what we had in ABCD compared to the verbal and back task. So here you can see that for both internal validation and external validation, our top performing stacked models outperformed single models. So stacking helped boost the prediction, not only overall prediction, but also the prediction within each of our ADHD groups. And finally, we also looked at the feature importance of our models, both single and stacked all. I'm going to just explain the stacked all, which shows that n-back task, 2 minus 0 back contrast, contributed the most to the prediction of our stacked all models, which was also the best model that we had. Also, out of the 10 best features that are contributed here, most of them are functional MRI, which is interesting. And finally, if we revisit back the questions that we had at the start, our top stacked models showed the significant difference that we were seeing for the observed cognitive functioning scores between non-ADHD and different ADHD tiers. And also, when we looked at the performance, we could see that most of our stacked models show no significant difference in performance between ADHD and non-ADHD. And also, we could see that the boost that comes from combining different modalities, neuroimaging modalities, was not only seen in overall performance, but also within each of our ADHD groups. And when it comes to generalizability to unseen data, we can see that some sets of features or models performed better than the others in an unseen data set. And also, it seems that task characteristics matters. So if we're gonna directly apply these models into like clinical settings, we might want to make sure that the task demands and acquisition characteristics are closely following the model trained on. And finally, I think it would be interesting to test this on a bigger clinical data set to see whether these findings hold or not. So thank you, and I have a poster session. I'll be happy to talk there.
We have time for a question.
Actually, have a question. Good. Is it working? Yeah. Oh, yes. Thank you so much for the talk. When you show the distribution of the observed and predicted cognitive scores across the different, yes, that one. So the effects that you've got there are similar. That's great. But the distributions are quite different in shape, and just wondering whether you think that's just, imprecision in the methodology, or what might that mean? There's for the blue one, it even seems bimodal, and maybe the green as well.
So we haven't really investigated why we could see that, and that could be, I think, a number of factors. And most importantly, if you look at the predictions, So we are still on like 57.57. So for the accuracy, the correlation that we get. So I'm not really sure why we get that, but we're not getting that high correlation for me to say that they should exactly be similar. So we have a long way to go for that.
Yeah, and also the sample size decreases as you go down.
Because it's more strict, and then we do not have teacher ratings for many people, so it just dropped a lot. So it's a bit hard to interpret that.
Yeah, so
and also there is a difference in standardization. So for the observed values, I'm just presenting the raw scores, but we standardize when we put it in the model. So there's also some differences in how the data is presented.
Okay. Thank you.
Thank you for the great talk. I was wondering what is your interpretation for the two-back task to be the most predictive in discriminating your classes?
Well, this is something.
ADHD.
Yeah, this is something we have found, in general, n-back task and 2 minus 0 back in specific is highly correlated with cognitive functioning, even if you look at healthy populations, HCP dataset and others that we have tested on. So in general, it seems that it's one of the highest, it highly predicts cognitive functioning. And then we cite that it also performs similarly between ADHD and non-ADHD group, which means that it probably captures the cognitive functioning variability from normal to abnormal instead of just being specified to one of them, which also I think aligns with RDoC initiatives. And there's a spectrum, and that captures it. Yeah.
Thank you.
Thank you.